Hello everyone, myself Jubea Triceliet, faculty at Silvers Public School, Kozhikode. In the last session, we have discussed about the physical properties and the electronic configuration of the 3D series. Today, I am moving on to the variation in the atomic size along the 3D series and down the group. So, before going to the next section of the atomic size along the 3D series and down the group, we should know what are the factors affecting the atomic size. The factors affecting the atomic size are effective nuclear charge and screening effect. You might have heard about these words. I'll give a simple manner explanation. What is this effective nuclear charge and what is the screening effect by considering examples in our daily life. When we are considering the effective nuclear charge, you just imagine a classroom. A teacher standing there and the students are being seated in the benches given there in a row manner. So, you can consider the teacher as the nucleus, the benches as your shells, and you are the students are the electrons. So, in a classroom, what happens generally? A teacher has a good control over the whole class. Especially, the teacher will be controlling the students who are sitting at the back. In our classes, sometimes we feel to sit at the back. Why? We prefer the back bench because we can be distracted when the teacher is taking class. But the teacher always keep an eye at the students who are sitting at the back because she never wants them to get distracted. So, there is a controlling manner. That is, there is some force, there is some attraction there. Like that, inside an atom, you consider the teacher to be the nucleus, the students to be the electrons. So, the nucleus will always have a force of attraction towards the outermost electrons. Inside a class also that happens. Those who are sitting in the front bench, we never used to bother because they are just sitting close to us. But those who are sitting at the back, always the teacher will see what is happening there, will keep an eye at that students. This is because there is a controlling effect. Similar manner in an atom, the nucleus has a force of attraction towards the outer electrons. This force of attraction of the nucleus on the outermost electron is called the effective nuclear charge. So, the electrostatic force of attraction between the nucleus and the valence electron is your effective nuclear charge. Now, we will move on to the next point, that is the screening effect or the shielding effect. Just imagine a celebrity is coming to your town. So, you also have a feeling to go and meet the celebrity, isn't it? So, on that day, you also will go to that place. So, what do you see in that place? You can see the celebrity will be somewhere at the middle and people will be all around the celebrity. You see a big crowd there. But the celebrity will always be surrounded by certain people wearing a black color dress. Who are those fellows? They are the bouncers. So, always it can be a heroine, a hero who are considered to be here as a celebrity. That celebrity will be surrounded by bouncers. What is the role of these bouncers? The bouncers will always push backward the people coming forward because the crowd always have a tendency to come near the celebrity. They just want to see the celebrity. That is their main intention. So, what do the bouncers do? The bouncers will push them backward. So, now just see, the people are coming forward, the bouncer is pushing them backward. So, there is a repulsion, isn't it? And at the same time, the celebrity will be looking at all the people around. So, there is an effective force of attraction, or there is an attraction from the celebrity side to the people because all of them are looking at the celebrity. So, you can see the celebrity is looking at the people is trying to come near the celebrity, the bouncer is pushing back. So, this repulsion is called the screening effect or shielding effect. Now, how can we put the same example to the atom? When we consider the atom, inside an atom you have the nucleus which always takes care of its electrons. That is, it has an effective nuclear charges there. And the electrons which are inner electrons are there and you have outer electrons. The inner electrons has a role of these bouncers. Inner electrons don't allow this outer electrons to come forward. The inner electrons always pull, the nucleus will have a force of attraction, the inner electrons push them backward. They won't allow this outer electrons to come forward. So this is called as shielding effect. So what happens? The nucleus, that force of attraction, even though the nucleus is having a good force of attraction, it sometimes cannot even hold tightly the outer electrons. This is your screening effect, or you can even call it as a shielding effect. The phenomena which occurs when the nucleus reduces its force of attraction on the valence electrons due to repulsion of electrons in the inner shell. Actually, for shielding effect, the inner shell is the main role there. They are not allowing, they are shielding. Outer electrons experience attraction from the nucleus and repulsion from the inner electrons. Just see, the outer electrons, they have an attractive force towards the nucleus, but the inner electrons are acting like a bouncers. Now, we are having S, P, D and F subshells. So, how are the shielding effect for these? S will be having the highest, then the P, D and F. D and F is having imperfect shielding. So, I shielding effect is when you have electrons in the S subshell. Then even in the P also, they can also shield. It is based on their peculiar size. S is spherical, so the shielding effect is more. P is having 2 lobes. Shielding effect is slightly lower than the S, and D and F have diffuse orbitals. Now, this is a pictorial representation of effective nuclear charge and straining effect. You can see the black colored lines here, the arrows which shows the force of attraction of the nucleus towards the outer electrons, and the blue color shows the repulsion. This is something that happens inside an atom. Now, we will see the atomic size along the period. If you are moving to the atomic size along the period, you can take the same example. You have the teacher at the center and the students being seated inside a classroom. Now, a classroom means it's something not a huge one, it's a smaller one. And in this, when one student wants to move out from the class, the student should ask permission from the teacher, because the teacher has a control over the whole class. She is having a control because the size of the class is also smaller. Imagine the same teacher taking a class from the auditorium. The auditorium is a big one. So, what happens there? The teacher can see the students who are sitting in the front, maybe till the middle. But those who are sitting in the back, they can even move out without asking permission from the teacher. So, teacher wants to get an attention from the students who are sitting at the back, or the teacher wants to control the student, but the size is very big. And the students who are sitting in front will shield the students sitting at the back, or the students sitting at the back cannot see the teacher because of this many students are being seated in the front. In the same manner, you consider the atom. Inside an atom, that happens. Inside an atom, when the number of shell is increasing, you have a nucleus, you have electrons, electrons are placed in a shell. So, as the number of electrons are increasing and as the number of shell is increasing, what happens? It will be very big. When it is very big, which have a more role there? Your screening effect or shielding effect. When it is very big, even though the nucleus is having an effective nuclear charge, it couldn't control the outer electrons. As the teacher couldn't control the students at the last bench in an auditorium, same thing happens here. The nucleus cannot control the outermost electrons because the number of shell is more, and the inner electrons will surely shield the outer electrons. But inside a class, the shell is not increasing. The number of desks and benches is, you may have 10 rows or 5 rows or 6 rows, it's always constant there. It is not changing. Even though the number of students increases, the teacher will have an effective nuclear charge there. So, when you move along the period, we can see that the number of shells are same. The number of shells are same, the number of electron increases and the number of proton increases. So, once the number of shell is same, the effective nuclear charge, even though the inner electron shielding and all is there, the effective nuclear charge outweighs the screening effect or the shielding effect. So, what happens? If there is an effective charge means, effective nuclear charge means it will hold the outer electrons very closely or very tightly. When it holds the outer electrons very closely and tightly, the size of the atom becomes smaller. So, along the period, the size decreases. The atomic radius decreases across the period because valence electrons are being added to the same energy level. At the same time, number of protons increases in the nucleus. The increase in the nuclear charge attracts the electrons more strongly, pulling them closer to the nucleus. So, what is the main point here? The effective nuclear charge outweighs the shielding or the screening effect. So, if the effective nuclear charge outweighs the screening or shielding effect, surely the size will become smaller. Now, we will look at the 3D series. I have shown a graph here. In this graph, I have shown all the elements, that is the 3D series elements along the period. Now, just see, according to our concept, the size should decrease. So, you cannot expect a graph like this. It should be something going from the top, it will go down. It will be just like a slanting graph. But here the graph is having a curve. Why is it like this? We will move the attention to the 3D series from scandium to Xithin. From scandium to Xithin, just see, from here, see the graph, from scandium till your iron, it is decreasing. So, our concept rule that effective nuclear charge outweighs the screening or shielding effect happens here. That is why it is decreasing. But see, after that, it is somewhat constant from iron to cobalt to nickel. It is something constant. Why is it like that? When you have studied the electronic configuration. So, in the configuration, you have seen the pairing starts from iron. From iron onwards, pairing starts means more number of electrons are coming. When more number of electrons are there, the atom will try to expand. So, along the period, there is an effective nuclear charge. At the same time, when the electrons are entered more, you are having 3d6, 3d7, 3d8, more number of electrons, the atom will try to expand because of electron repulsion, which is due to the pairing. That is why you see that the size is somewhat constant. They do not have much variation. Both the effect balances each other. But when you reach copper to Xithin, again the size is increasing. This is not the case along the period. The general concept is different here. Why is it? In copper and Xithin, you have completely filled d orbitals, that is 3d10 is seen in copper, even in Xithin it is 3d10, that is maximum number of electrons. When you have maximum number of electrons, electron repulsion is so high that the atoms tries to expand. That is why you see a slight increase in the atomic size from copper to Xithin. The first point has been explained and written here, that is from scandium to Mn, the size decreases as the effective nuclear charge outweighs the screening effect. Second point, from Fe to nickel, the atomic size remains constant. This is because the effective nuclear charge tries to shrink the atom, while the increasing in the number of electrons in the d subshell causes the size to expand. And the two opposite forces balance each other. That is why it is having a constant size. But at the end of the series, you see there is an increase in electron repulsion, which makes the atom to expand. Now, we will move the last point, that is atomic size down the group. Atomic size down the group, you know that coming down the group, number of shell is increasing. Imagine your auditorium class, the number of shell is increasing. So, whose effect will be outweighing here? The shielding effect outweighs the effective nuclear charge, because down the group the number of shell is increasing. So, as the number of shells increases, what happens? The shielding effect outweighs the effective nuclear charge. It doesn't mean that the atom is not having an effective nuclear charge. The atom is having the effective nuclear charge, but because the size is bigger, because the number of shell is bigger, the effective nuclear charge is being outweighed by the screening effect. That is, the screening effect outweighs the effective nuclear charge. Here you can see the number of shells increases, number of electrons increases, electron density increases, repulsion of the electrons increases. So, as we move down the group, energy level increases, electron density increases, so electron repulsion increases. Therefore, the atomic radius increases as we move down the group. That is, the shielding effect outweighs the effective nuclear charge. Now, we will move on to the atomic size down the group of the 3D series. Now, generally we know that down the group size of the atom increases. But what happens in the 3D series? 3D series means you have to see the size of the atom down the group. So, you have to consider the 4D, the 5D, all the series. So, this is generally not just the down the group 3D series, it is just the atomic size down the group of transition metals. We include the 3D series here, but we have to consider the 4D and the 5D, then only the size is increasing down the group. Why is the size increasing down the group when you move from your titanium to zirconium? I will take those elements. The 3D series I have taken titanium, the 4D series it is zirconium, and you have your hafnium in the 5D series. So, when you move from the 3D to the 4D and then to the 5D, what is the change in the atomic size? When you move from the 3D series to your 4D series, the size increases. Why? We know that the shielding effect or the screening effect outweighs the effective nuclear charge. But from zirconium to hafnium, that is from the 4D to the 5D, we see that it is not as we expect. It is found that the size of hafnium is smaller than zirconium. How can it happen like that? We can just see the electronic configuration of zirconium and hafnium. Just see zirconium, it is krypton 4d2 4s2. But in case of hafnium, it is xenon 4f14 5d2 6s2. That means, can you see a new subshell there, the 4f? In hafnium, the 4f is being completely filled. When you have electrons, what happens? 4f has imperfect shielding. That means the nucleus can hold the electrons in the outermost shell. Now, in the case of hafnium, the 4f subshells are being completely filled and then only you are filling your 5D. So, when the electrons are there in 4f, the shielding effect is very poor. So, the nucleus can hold the outermost electron. So, if the shielding effect is poor or if it is having an imperfect shielding effect, what happens? Effective nuclear charge increases and the size decreases. Size increases from titanium to zirconium, that is titanium is in the 3D and zirconium is in the 4D. But it decreases from zirconium to hafnium due to a term is mentioned here, lanthanoid contraction. What is this term? I told you that you are filling your 4f then only your 5D. So, this 4f has imperfect shielding. Imperfect shielding means the effective nuclear charge or the nucleus holds the outermost electron and the size decreases. Size decreases means contraction. This happens after the lanthanum. Because after lanthanum in your periodic table, you are filling your F block elements. So that is why you use the word here, lanthanoid contraction. Why is from zirconium to hafnium the size decreasing? It is because you have filled the 4f orbital completely. When the 4f is being completely filled, what happens? Effective nuclear charge increases because the 4f has imperfect shielding effect, and this effect is called the lanthanoid contraction. The lanthanoid contraction is a filling of 4f before 5d. Very important point. And the 4f has imperfect shielding. Due to this, effective nuclear charge increases, size decreases. Because F is having very poor shielding effect. Imperfect shielding effect of one electron by another in the same set of orbitals, that is the same set of F subshell, is very poor. It has imperfect shielding effect. The shielding effect of one 4f electron by another is less than that is found in one d electron by another. So, if nuclear charge increases, size decreases. That is, when you consider the F and the D who has imperfect shielding, it is for F. So, if you have more electrons in F, they will be having very poor shielding effect. Now, I go on to the questions related to this topic, and this topic is a very important topic for class 12 board exams. So, I will be discussing some questions which is asked in the previous years for the class 12 board. The first question is, the atomic size is constant from Fe to nickel. Why? We saw the graph. In the graph, the atomic size was constant. Why? The two opposing forces, that is the effective nuclear charge as well as the shielding effect, balance each other. When they balance each other, the net effect is size is constant. That point is very important for your board exams. Next, the atomic size increases from copper to Shithin. Yes, we saw there's an increase in the graph. Why is it like that? Because they are having completely filled d orbitals. Copper and Shithin have completely filled d orbitals. Now we shall move on to the next question. The question number 3, explain the variation in the atomic size along the period. When you see such a question for the board exam, it can be for a 2 marks or a 3 mark question. For this, you have to first draw the graph, where you see that there is a curve in the graph, and you know that from scantium to your iron, the size decreases because the effective nuclear charge outweighs the shielding or the screening effect. Then you see in the graph that it is constant from iron to nickel. This is because the two opposing force, the effective nuclear charge and the screening effect, balance each other. So, when you draw the graph, after that you have to mention this point. And the last point is from copper to Shithin, there is an increase. So, for that, why is that increase seen? It is because of the repulsion. That is, there is electron-electron repulsion, more number of electrons. So, what happens? The atom tries to expand. So, you have to draw the graph, write the 3 points, and you can score the full mark there. Next, you are having zirconium and hafnium having similar size. Justify. In 1 mark question, you can just write lanthanoid contraction. If it's for 2 marks, you just have to write what is this lanthanoid contraction. It is the filling of 4f before 5d. 4f has imperfect shielding. So, since 4f has imperfect shielding, effective nuclear charge increases, size decreases, and that is your lanthanoid contraction. Next, again the question can be even directly explain lanthanoid contraction. So, you have to explain the lanthanoid contraction and then tell that one of the consequences of lanthanoid contraction is zirconium, hafnium having similar size. So, question number 4 and 5 can be asked as a related question together or as a separate questions. When we move on to the last part, that is just to summarize everything. We have explained the factors affecting size of the atom, the effective nuclear charge and the screening effect. Then we told about the variation of atomic size in the 3D series, that is along the period and down the group. So we know that these elements are very important in our day-to-day life. So we should know more about these elements. In the two videos, we have already gone with the physical properties and electronic configuration, and even in this we have gone with the atomic size. So it is a very important part to know more about the 3D series elements and their uses and their properties. Thank you.